Okay, at this point, we've adequately covered the concept of the nucleophile, so we need to turn to the electrophile. And there's just going to be one video in this area. An electrophile is a massive component of organic chemistry. It's equal in importance to the nucleophile, but I think in most cases easier to understand uh, in general. So I've written the definition at the top of the screen, and let's just summarize it. This is going to be any atom that is electron deficient, and that can come in two different forms, really. You can have atoms that are literally or literally have the absence of electrons, and those atoms are going to have formal charges on them that will be equal in magnitude to however many electrons are missing. In organic chemistry, most of the time, 99.999% of the time, these types of electrophiles are going to have a +1 charge on them. Other types of electrophiles, and more commonly speaking, if you will, I think that's probably fair, is that the electrophiles are going to have a partial charge on them. And this is going to be because that particular atom is bonded to another atom that has a difference in electronegativity. Predominantly, the atom that the electrophilic carbon is bonded to will have an electronegativity which is higher than the electrophilic carbon, withdrawing electron density to itself and causing the electrophilic carbon to have a deficiency in electron density and therefore carrying a partial positive charge. By definition, any kind of an electrophile is also a Lewis acid. And Lewis acids are defined by the fact that they accept electron pairs. So if you think about that for a minute, this should make sense to you in terms of organic chemistry, because organic chemistry is all about forming bonds between a nucleophile and an electrophile. And the nucleophile brings to the table a pair of electrons that's available to form a covalent bond. And the electrophile is going to accept that pair of electrons in order to form the covalent bond. Now let's go through the types of, I'm going to give an example of electrophiles here. And again, in the laboratory, you guys have worked with all of the examples I'm about to go through, every single one of them. All right, the first is going to be the classic carbocation. The most important, if you will, not second, but at least 50% of the importance of an electrophile that's due to partial charges. The carbocation is special because it only has, the carbon center only has 6 electrons around it, which causes the carbon to have a formal charge of literally +1. The reason why the carbocation is so important is because of its geometry. It is sp2 hybridized, it's trigonal planar. And the significance of this is that when you bring a nucleophile in, because this thing is planar, the nucleophile has very easy access to the positively charged center, right? This is a triangular plate, and that means that the nucleophile literally has 2 completely open sides to pick its attack from. So the carbon electrophile, the electrophilic center, the carbocation, has excellent accessibility. All right, the next type will be the electrophilic carbon, which is due to a partial charge difference. So in this case, I'm going to stick to a really easy example, iodomethane. All right, and it's where we have a methyl group which is attached to iodine. So we remove one of the hydrogens and substitute the I. Now, because there's an electronegativity difference here, the I takes on a partial negative charge because the electron density in the covalent bond is shifted to the I. Subsequently, the carbon in this has a partial positive charge on it. That makes this an electrophilic center. Now, in terms of the influence of the iodine, your electronegative atoms have an electrophilic effect on the most immediate atom that they're bonded to, right? That's where the magnitude of this partial positive charge is going to be highest. But the influence of the iodine also carries over to at least one more bond length. So that means that, I'm going to just change my color here a little bit, that these hydrogens are also electrophilic. But the magnitude, of course, is going to be less. And you guys have had physics, so you know that, electrical charges fall off dramatically, the more distance that they occur from whatever's generating the charge differential in the first place. So these positive charges here are going to be less in magnitude than the main one that is on this carbon. So this is another example of an electrophilic center, but what you have to pay attention to here is that this is sp3 hybridized. So the carbon in this case is tetrahedral, or the geometric arrangement around this carbon is tetrahedral. And what that means is that the accessibility of this carbon is going to be varied. It's going to depend what's bonded to it. In this case, with the hydrogens, this carbon is readily accessible, not as accessible as a carbocation, but this is readily accessible in the condition that it's in. However, if we start switching out groups here and we take the hydrogens out and we add other R groups, like for example, we could pull a hydrogen and put a methyl group in here. As we add subsequent, what I mean to say is as we add successive R groups here, then the accessibility of this carbon electrophile is going to go down substantially. And you guys have got experience with this too. We're going to deal with the elimination mechanisms coming up, and you guys have done eliminations, and the basis of the elimination is providing an electrophilic carbon that is obstructed. So when the nucleophile comes in and tries to get in here, it can't, and so it interacts with a hydrogen instead, and that's how you end up with double bonds and things like that in molecules. In this case, where we have all hydrogens, the carbon here is got excellent accessibility, and the molecule that we're looking at happens to be one of the hottest electrophiles for SN2 reactions, which will be the first mechanism that we deal with. Now, another type of electrophile here that you also have dealt with a lot in the laboratory is the classic carbonyl carbon. And I'm just going to define this atom out here as being X. It could be hydrogen. I mean, all right, let's just to be clear, it could be a hydrogen, it could be a OH, it could be R, like as in some type of alkane, whatever, all right? But again, we have the bond between a carbon and an oxygen. The oxygen is very electronegative, second only to fluorine in the periodic table. It's arguably the second most electronegative atom in the table. So this is got a very high magnitude delta negative. And that makes our carbon down here partially positive in a big way. Now, the other thing that makes this electrophile super important in organic is that it is sp2 hybridized, which again means that it's trigonal planar. And that's super important because again, this carbon is going to be super accessible. Why? Because it is part of a triangular plate. So the incoming nucleophile is literally going to have two completely open surfaces to pick from in order to make its attack on this electrophilic carbon. Again, can the R group over here and the X group over here influence accessibility? Of course it can. But still, because this region in the middle here is sp2 planar, the accessibility is still going to be better when you compare it to a molecule like this one over here, where it's tetrahedral and you have an atom literally that is sticking out spatially in all directions. So as soon as you start to exchange out these hydrogens for other groups, the accessibility of an sp3 carbon in this case is going to be significantly less than if you switch out the R group in the carbonyl example over here and the X group. If you're switching these out and you're making them more complex, this carbon is still going to have more accessibility than the alternative options next door to this. Okay, and let me just go to this last screen because I think I actually covered the other thing that I wanted to. So when we talk about, because this term is going to come up, and I'm misspelling it right out of the gate, no surprises there. So when we talk about sterically hindered, I think there's two L's in it. I don't know. You guys will have to check. Sterically hindered carbons. That's the concept that we were talking about in regard to what these groups are. So if we go back to the methyl group really quick, and we put some kind of an electronegative atom on it. So this is a little different than the other example, but same concept. All right. When we talk about sterically hindered electrophiles, and remember this concept, we talked about it with the nucleophiles too. It cuts both directions. All right, when we talk about steric hindrance, what we're talking about is accessibility to the electrophile. So it's accessibility to electrophile. And this is a super important concept because as soon as you start to substitute out the groups that are attached to the carbon, so these guys here, now all of a sudden the kinetics of the reaction, in other words, the ability of the nucleophile and the electrophile to interact are going to be influenced. And the result of that could be anything from no reaction to side reactions that you don't want. All right. Again, so I think that the biggest influence in terms of sterically hindered carbons has to do with the ones that are sp3 hybridized. That's fair to say. This group here you have to pay attention to the most because the nucleophile is in order, and we'll talk about this in more detail when we start into the mechanisms, which is going to be the next lesson. The nucleophile has to have entry to backside attack in terms of sp3 electrophiles. The nucleophile cannot come in from the same side as what's going to turn out to be what we're going to be calling the leaving group. This is sort of an intro to the next topic. Because this dude has to exit this way. And so you can't have a nucleophile coming in on the same side as a group is going to have to leave. They're in the way, all right, of one another. So your nucleophiles when they're interacting with an electrophile that's sp3 has to come in from what we call the backside attack. And so you can see right away that what you have bonded to that carbon is going to influence the ability of this guy to get in. All right, now with that, I'm going to go ahead and close the video.